So just like to thank the organizers for inviting me to speak and for the opportunity to visit this beautiful city. And what I'm going to do at the beginning is just say some motivation. There's a fair number of students, so I just want to spend maybe a minute talking about this. So if I have any representation from G, I mean, it doesn't even have to be GLN, but GLN to GLV, then it is a sub of the standard representation to some power tensored, the dual of the standard representation to some power by a theorem of Chevalley. So what this tells you is that if we are looking at Langland's functoriality, then it's very important to understand the case that corresponds to the tensor product. So if we knew functorial transfers attached to this tensor product, then we'd have cut sort of a wide swath through functoriality. And then, as Frieden mentioned, and one of the points of departure of the Braverman-Kazhdan proposal is that, well, by converse theory, what do you need to know in order to establish functoriality for this? So to understand, you would want to know the analytic properties of triple product L functions plus converse theory in the sense of Piatetsky, Shapiro, and Cogdell. So when I say triple product L functions, I just mean instead of 2 copies here, I want 3 copies here. So this is the point of departure and sort of the meta reason for looking at this case. All right? So I want to give maybe too ambitious outline of this talk. What I'm going to do is I'm going to, well, F will be a number field. I'm going to construct some space X over F with a group action. I'm going to define some Schwartz space on this space and a Fourier transform and prove a summation formula X over X of F of X equals sum of the Fourier transform on X, F of X, X in X of F. This part is joint with Baiying Liu. Now, using this space, I'm going to form a zeta function. I haven't defined any. It'll be, yes, it'll be an affine space. Yeah. So, and I'll say precisely what it is. I'm going to give you a zeta function using the typical Godemont-Jacquet type procedure in this space that has a functional equation. And the funny thing here is that it's not going to be Eulerian. It's going to turn out that I'm going to be able to write this as the sum over beta in f cubed of some z beta, where these things are Eulerian. All right? So up to this point, everything that, I mean, I've written all this down, and this is on solid ground. I mean, this part has been submitted for publication. But then my current work is on computing what these things are. So I can give you a computation of these things in terms of the Whittaker model, but the point that I'd like to make is that if I look just at one term of this, then this is related to L of S pi 1 tensor pi 2 tensor pi 3, where pi I are on GL3. Yeah, I mean the Drankin product, so. All right, so I mean that's sort of so this is an outline of what I'm going to try to do. So let's start with the space. So this is groups and orbits. All right, so I'm going to take GL3 and I'm going to let it act on UI this is the standard representation. U will be product from I equals 1 to 3 of ui. I mean, this is just for an index. That's why I'm using the i's. So for R and F algebra, I'm going to define a scheme YR is UI wedge in U check cross U of R such that U1 check of U1 equals U2 check of U2 equals U3 check of U3. All right? So this is a very degenerate case of the following situation. You give yourself 3 quadratic spaces, and you say you look at the subscheme that's cut out where the 3 quadratic forms are equal. Right? So this is just a very degenerate case of that. This is the split case. Now this thing admits an action by a certain similitude group, but for my purposes it's more convenient to restrict that to a Levy subgroup of that. So let me talk about the group that I'm going to have. This is the first whiteboard I've ever used that actually works. Okay, so, right. So my space X is going to be U cross, Y cross U check. I'm going to let G be GM cross GL3 cubed. And I'm going to have an action G cross GM cubed cross X to X. And it's sort of the, I guess you could probably guess, but let me write it down. So standard action of G. All right, so I have the standard action of G, and then I have these 3 copies of the multiplicative group that are acting on this last copy. This lambda is just 1 copy, and it's acting diagonally on the 3 copies. Okay? All right? So that's my space. All right? And let me... the space is sort of nice, and I want to talk a little bit about its structure. First, let me write down the generic stabilizer. So inside G cross GM cubed, I have this group Q. Q of R is 1, A, 1, B, C, C inverse, or A, C, Rn, R times cubed, and B is an R cubed. All right, and for beta in R cubed, I want C beta to be 0, 1, 0, 0, 1, 0, 0 beta 1. So this is, I'm thinking of as a point in X of R. Okay, so then there's, there exists an open immersion from Q G cross GM cubed. Sorry. Yeah. Right. So lambda is a scalar, right? And there's what? It's 1 scalar, right? So I'm looking at the subscheme where all the quadratic forms are equal, right? So you have the 1 scalar that's acting base. It's a similitude factor, essentially. And so this is acting diagonally on that. But this is 3 numbers. So if I wanted to write this out better, I could write, yeah, so 3, this would be lambda. It's G cross GM cubed. G is GM times GL3 cubed. Yeah, so, sorry, I mean, there's, yeah. So then let me just and then U, and then on the last factor, it's there's 3 H's. Yeah. Okay. Right, so GM cross GL3 cubed cross GM cubed, so we have lambda GH. Okay. Sorry about that. Okay. All right. So anyway, I take this space and I map it into X via G. Well, let me write it this way since use the same coordinates. Lambda GH. Oh, sorry. There's one more factor here. Cross GA cubed maps to lambda GH C beta. Okay. So notice I have just GM cross G cross GM mod Q and a GA cubed here, right? So what's the point of this? The point of this is that this space X is not spherical. However, it's related to a spherical space in a very nice way. So X is not spherical, but it's birational. All I mean is it has an open subscheme that is the same as G cross GM cubed spherical cross GA cubed, right? So it's a spherical space times something that's an affine space, all right? Okay. And the fact that we have this affine space here is the reason that we're having this sum over beta in this zeta integral that I wrote down at the beginning of the talk. Okay. This space, it's the beta. It's the beta. So, right. Okay. So, all right. So now let me talk about short spaces. All right, so we have the usual short space of U check. All right, so, and it has a Fourier transform F U check from S U check AF to itself, and it has a Poisson summation formula, right? It's just a vector space after all. All right. But the other space that's appearing here also has a short space. So Byang, Liu, and I defined a short space S of Y AF plus Fourier transform Fy. And let me write down as a theorem because so for nice F, you have some Poisson summation formula. Okay, so all right, and I don't think I'll have time to talk about this. Maybe at the end I'll say something about how this works, but I want to highlight that. Essentially, what we do is we choose the F to kill some natural boundary terms that should be in here. And to get the full results in what I'm trying to do here, we really need to get rid of those assumptions. And it comes down to One of the obstacles is actually getting rid of some of the assumptions in the work of Braverman and Kazhdan. As I understand it, Diwa has a student who is working on some of that. But anyway, so we have this Fourier transform, and I'll just mention that it's important to remove the nice assumption. So we have to work with functions that aren't very nice, but yeah. Okay, so now let me define the zeta functions. So this unfortunately requires some notation. So, all right. So I'm going to give myself pi, which is pi1 tensor pi2 tensor pi3 on GL3 AF cubed. I'm going to give myself a character eta of GM. Actually, let me say quasi-character, not assuming that these are unitary. Sorry, C times. Okay, so this is a one variable thing. This is a 3 variable thing. Omega is the central character of pi. I'll give myself some vector in the space of pi. I'll give myself a function f in the algebraic tensor product of these two short spaces. All right. And let me just, I mentioned it, but let me say one more time that I'm not assuming that these are unitary. Not assumed unitary. Okay. All right. So, I mean, as usual, you can write your character eta as a unitary character times S eta, where eta u is restricted to the copy of the real numbers inside GM is equal to 1. Okay. And when I talk about something being holomorphic in say, eta, I mean that it's holomorphic in this S eta, right, the standard thing. Okay. So here's the zeta function. The zeta function is z phi f eta chi equals phi of g sum over c and x of f lambda g h inverse c eta of lambda I of h dg dh d lambda. Okay. So, I mean, all I'm doing here is I'm taking my cust form and I'm integrating against my formula, but I also need to weight by some characters corresponding to the similitude factor lambda and then these other h's. Okay. So this is sort of a many variable gadget. Okay. All right. So here's the theorem for this. For nice f z phi f chi, or sorry, what did I say? Eta chi. Eta chi admits a holomorphic continuation to the S omega S eta S chi plane and satisfies some functional equations. So this is sort of a many variable gadget. So we get actually a lot of functional equations, but let me write down the two that seem the most interesting. All right. So z phi f chi eta equals z phi chi, let's see, eta inverse omega chi inverse. All right, and here this notation chi is just chi 1, chi 2, chi 3. Remember, chi is a three-variable gadget, but I can get a one-variable gadget by multiplying the three quadratic characters together. And then the other functional equation that I'll write down is f okay. All right. So you have these. I mean, if you stop and think about it, you can see what's going on with this. So we have, if we just think of U as one gadget, just one vector space, we have two Fourier transforms in play. We have a Fourier transform for the space Y, and we have a Fourier transform for the space U. And for both of those Fourier transforms, we have a functional equation. And so this is the functional equation for the space Y, and this is the functional equation when I apply both of them. And this little operator here is just taking the variables in the function and switching them. So the proof of this is actually, I mean, once you have these Poisson summation formulas, the proof of this is just follow Gaudemont and Jacquet following Tate. It's essentially the same argument. No, I didn't define any of them here. So, I mean, one of them is, so the cheating one is just the usual Fourier transform, right? Yeah, we'll see. I may have time to actually get into what the definition of this is. So the definition of the Fourier transform for Y as it stands is somewhat indirect, and it would be better to have an intrinsic definition of it. Yeah, go ahead. Right. Then I get 0 equals 0. So what happens is if you take Y, then the generic stabilizer is going to look, in one factor, is going to look something like 1 GL2. And when I integrate a cos form on GL3 against this subgroup, then I get 0. It's a vanishing period, right? So you're forced to fatten up or enrich the space that you're working on. Now, I tried for many months to try to fatten it up in such a way so I didn't have this GA floating, this extra affine space floating around, but I was unable to do so. I think it still might be possible by taking this summation formula and cutting out that piece, maybe using something like the argument I used in this paper on, well, summation formula for zeros of a quadratic form, but I don't know how to do that. Okay. I have no idea. I haven't checked it. I think my feeling is that because the two summation formula don't know anything about each other, that the two should commute, but I haven't checked it. I have no idea. I have not checked it. But that's my hunch because they're two different, it's an interesting question, but I just haven't gotten to it. But because the Fourier transforms don't know anything about each other. It's one space times another space. So, I mean, yeah. So let's see. So let's compute what these. Okay, let's see what the meaning of this thing is. So here's section 5. This is Z as a multiple Dirichlet series. Okay, so remember we have some open immersion from this space into X. All right, so using this, you can write Z of phi f chi eta equals sum over beta in f cubed of z beta phi f chi eta. Right? And let me define what those things are. I mean, I'm just breaking it up over the orbits. So. Right. All right, so z beta is the integral over q f g a f cross g m a f of phi of g lambda g h c beta. That's the same as before, so s eta cubed maybe. Okay, so this is just the, I mean, I'm breaking it up over the orbits of this group action, and this is the part corresponding to a particular orbit. So unlike the usual theory of integral representations where you want a finite number of orbits, you're not so lucky here. There's infinitely many orbits. All right, so here's the proposition though. Each one of these orbits has a nice formula. Giannis helped me with this last semester, although if it's wrong, it's my fault. So, G AF cross AF times cubed. So you take the Whittaker functional of G times F lambda G H C beta times chi H eta 3 lambda D of whatever. Okay. So if you look at what this, if you unfold this integral, then you get an integral of the Whittaker function of your form times this weighting factor, and you're sort of taking an orbital integral that involves the Whittaker function and then your starting function. Okay? And this is just sort of an easy unfolding, and this is the reason that the group Q is, the reason that the representative of the orbit was chosen the way that it was so that you got this nice formula. Okay? So the point of this is that this is an Eulerian object, right? So the Whittaker function is Eulerian, and so is this. So this is something that one can compute, at least at the unramified places. And that bit of one can compute is what I've been doing with my, keep me off the streets, I guess. So, oh, sorry. I just mean eta 3 lambda is eta. I'm just shifting it. Yeah. The reason I did that was to make the functional equation look nicer. So. All right. So now the game is to compute these things, which in principle is, I mean, it's fairly low rank, so you know, it will be done eventually. But let me, so for a long time I thought what you could do was choose a test function to isolate a particular point. And it doesn't look like that's possible at this, from what I'm getting from it. But, okay, but let me write down what you get if you specialize to sort of the easiest point to compute, which is when beta is equal to 0, 0, 0. So here's an example. So let me let I be the Langland's class of pi I. And I'm going to work locally for the moment. All right. So then the z0, 0, 0 of w naught f basic chi eta. I'm assuming everything is unramified here. It's equal to L of 0 eta to the fourth, make it inverse chi squared, L of, just write it down, product of L 0 pi I times L of 0 pi I wedge tensor chi I. All right. And I'll sort of interpret this for you after I write it down. And my apologies for the sort of, if you're latexing live, then this is a challenge for you right here. So. Okay. Times the product from I equals 1 to 3 of sim minus 2ki ai minus sim L minus 2k I minus 1 ai. Okay, so this is which is a product? Huh? So this is yeah, this is a times, right? So you have this factor times this factor. Is that? Yeah, and you sum over this whole thing. Is that the question? Yeah, you take the top and then it's times this. All right, so this is sort of, I mean, this is an easy factor, right? I mean, this is just the standard the L functions of the standard representation. And then you have this factor, which is some, I mean, so the K, I mean, this is some index set. I mean, I can write it down, but I mean, maybe it's not so important. Okay, but I mean, it's fairly concrete. But so I don't know how to analyze this, but one thing that makes sense is to say, okay, well, let's just assume that pi satisfies the Ramanujan conjecture and sort of see what the main terms are. Okay. Yeah, right. So where do you get the triple product out of this? So to do that, I mean, the expectation that seems the most reasonable is that one might be able to locate poles. So if you're trying to locate poles, what you care about is the leading terms in your L function. Okay. So if you look at so you want to care about the q to the negative s term in the L function expansion. And so if I just take this and if I look at it, I just truncate it, I look at up to q to the negative 2s, this is the following. So what I mean by this is this, if I take, well, let me put it this way, up to eta of var pi squared. Okay, so if I cut it off at this point and just look at the eta of var pi term of this, then what do you get? You get L of s pi tensor omega inverse chi eta tensor eta cubed over L of s eta omega inverse pi squared times the product from I equals 1 to 3. I apologize for using this notation, but part of this is, I mean, maybe somebody has some insight into how to analyze these things. So, okay, this is hard to read, but let me write it in symbolically as follows. That what this looks like is it looks like tensor cubed over tensor 0 times the product of tensor 1 over tensor squared. So what I mean by this is that if you just ignore all the terms that are sort of higher order in eta, then you get the tensor cubed L function divided by some character times the product over all the possibilities of just the standard representation of the pi i's twisted by something, and then the Rankin-Selberg of the various pi i's moving together. Are there questions on that? So now, this is one of the reasons why it seems like it should be impossible to isolate this term in the expansion, because then you'd be saying something like the zeros of this L function have to divide the zeros of the numerator, which is sort of ridiculous. Okay, but the point is that this information that we want to extract is there, and the question is how do you actually extract it? Right. So Z is Z of 0, 0, 0. Okay. So it is. So it is the. You're taking the orbit of the point. So you're looking at the orbit of this point in your space. So 3 copies, I guess. Right. So you just take you do the Godemann-Jacquet. I'll write it down if you want, but you do the Godemann-Jacquet thing and you integrate just over this orbit. What is the stabilizer? Right. The stabilizer for all the orbits is the same thing. It's Q. Right. So ideally, this would be what you'd like to look for. I mean, this is what you'd like to just have one copy. You'd just like to have the Q. So I mean, this Z 0, 0, 0 is you take your, it's the integral over, let's see, Q F G A F cross G M A F cubed of your automorphic data times your F, let me just call it FG, F of G dot C beta. C0, where this is C0. Is that, I mean, if I strip it, and perhaps I should write this way at the beginning, but you have to incorporate the characters in and whatnot, but this is the, right, so what you'd like to, so this is a perfectly legitimate spherical variety, and you would like to have a summation formula for just this orbit. I mean, according to your conjectures, that should exist. You've given yourself an affine closure of this thing, and so you should have a summation formula for it. But the point is, I can't do that. I can only do it after I sum it along this affine space. This thing? Probably not. Not this Z00. So it's probably only the sum. Yeah. Yeah, converges absolutely in the cone, and then to get the additional, to get that it's holomorphic everywhere, you apply the 2 Poisson summations. So it's, yeah. So I have to do your trick and say, well, if you remember from my last talk, this is the stuff I did with buying. So but I can't, I'm out of time, but I can explain afterwards how you get at that. But, and I think I'll, wait, I have 10 more minutes, don't I? Oh, okay, well, I can do it, great. Sorry. Okay. Okay, so let me talk about that. Right, so let's talk about this, let's try to explain this Fourier transform. Sorry, for some reason I thought I started. All right. Great. So the Fourier transform on Y is obtained via a very indirect method. So let me just talk first about Fourier transforms on Y. All right. So I start with a Braverman-Kazhdan space, which is, I'll call XP, which is SP6 mod the derived group of P, where P inside SP6 is the Siegel. Parabolic. This thing sits inside, you can use the Plücker embedding, which just amounts to taking the last three rows of your matrix and taking their wedge product, and you get a map into this affine space. So this realizes this as a quasi-affine space. And let me let xp bar be the closure of PL of xp. All right, so now what Braverman and Kazhdan do in, as sort of evidence for their program that's been mentioned today and we'll talk about later, they define a short space, xp bar of AF, and Fourier transform, and they prove a summation formula that I'll call this. So they prove the summation formula for F in their short space under some conditions. So this is for nice F. And it's very important to remove the assumption of niceness. So Baiyang Liu and I were able to give a general expansion of this, but the boundary terms are given in terms of residues of Eisenstein series. It would be better to give a geometric interpretation of that, perhaps using the Siegel-Bay formula. All right. So now what do we do with this in order to get the summation formula on Y? Well, I give myself an F2 that's in the short space of my quadratic space. I take the tautological quadratic form, and using this I get a Weil representation. All right. So what I'm going to do is I'm going to take, right, so I guess I need to say something. So I'm going to think of this as a representation of SL23. I'll call it rho. Okay. Now what I'm going to do is I'm going to form a theta function out of this and plug it into the integral representation of Garrett, PS, and Rallis. Well, Garrett classically and then PS and Rallis sedelically. Right, so I form theta F2G, which is the sum over Xi and U check cross UF of rho G, F2 of Xi. All right. And what I'm going to do is I'm going to take the integral over SL2 cubed of, let's see, rho F2G sum over gamma XPF of F1 of gamma G dG. Okay. Now, this thing unfolds. Okay, so what am I doing? SL2 cubed actually embeds with open orbit into this space. And this is how you get the integral representation for the triple product L function on GL2. So instead of plugging in three Cuss forms, what I'm going to do is I'm going to plug in three theta functions. Okay? So I plug in the three theta functions. And on the one hand, if I unfold this, I get something that I'll write as the sum over C in Y of F of I F1, F2 of Xi. All right. Where I is the following integral. So I of F1, F2 is integral over N naught AF SL2 cubed AF F1 rho G F2 C. right? Where this is the subgroup in here that is of the form 1T11, 1T21. Okay. Right. So the point of this, and maybe I'll omit some of the details, is that when you think about what the Weil representation is doing, when you execute this integral, you have to take each one of these xi that lie in your product of three vector spaces. When you integrate over n, it kills everything that's not in this subscheme y. The definition of the Weil representation, when you integrate over this subgroup, tells you that the three quadratic forms all have to be equal. So it's so that's sort of the crux of the argument, that you can do this. So you get this summation, you get that this integral is equal to this sum over y smooth. Now, you know a summation formula for this piece, because Braverman and Kazhdan give it to you. Right? This is one way of putting the sum of the theory of Siegel-Eisenstein series. Right? So then the summation formula in the Fourier transform works as follows. You define the short space in sort of this horribly ad hoc method to be the span of these integrals I, f1, f2, and then you define your Fourier transform to be the Fourier transform that's induced by this one. Which, of course, then you have to check is well defined, but you can do this. So the Fourier transform on y takes this to this, and it sends this integral to I of f x p bar of f1, f2. Right? So you get a new Fourier you get a new transformation formula from your old one. Okay? All right, so that's the answer to what this Fourier transform is. Now, of course, this isn't very satisfying because it's not somehow intrinsic to y, and it would be better if there were a way to phrase this Fourier transform that sort of didn't involve this other space. But, I mean, despite that, you can work with this and you can compute with it. It has some nice properties. The short space is going to contain the restriction of any smooth function on the vector space, and so there's a large supply of functions on this. And also, it's a procedure that I think is going to work in at least a few other contexts. Anytime you have an SL2 that's lying around in some integral representation, you can plug in a theta function. I have one of my students is working on this in a case related to B.L. Kaplan's thesis. Now, this sort of indicates some of the, so in order to fully understand what's going on here, we really need to remove this niceness assumption. And sort of the first place to start is how do you get a general formula for this? Okay. Now again, Bayang and I proved it, a formula for arbitrary functions where the boundary terms are given in terms of Eisenstein series. So the point then becomes interpreting those residues of Eisenstein series in terms of, say, I mean, Siegel-Weil seems like the knee-jerk reaction, but I'm not sure whether, and it might work for this. Yeah. So I guess now I'm out of time, so sorry about that. And thank you for listening. As far as I know. But I mean, it's a manifestation. I mean, I guess, yeah, I mean, I guess the new idea, the crux of the new idea is plugging theta functions in terms of where you would normally put a Cuss form in. Because then you get another variable to integrate over because the theta function has a whole nother variable, right? And this begs the question, I mean, is there some other, I mean, I asked Switek about, I mean, for higher rank covers, like, is there some analog of this? right? Or even just in this case for metaplectic covers, I mean, anytime you have some integral representation that involves a symplectic group, you could think about, does it make sense to plug in a theta function? The point is that the theta functions have you understand their Whittaker models, so that when you do some integral representation that computes the Whittaker model, when you compute the integral, sometimes it isolates some nice, like something involving the quadratic form. So, yeah. Oh, for this? So I had so my original goal was I wanted to understand the monoid, which is GL2 equals GL2 equals GL2 equals GL2, sorry, determinant equals determinant equals determinant on GL2. Just so I could figure out how to do that for GL2 cross GL2 via an analytic number theory argument. And then the idea was to extend that to GL3 using analytic number theory. But the analytic number theory method, I mean, it doesn't give quite as good a result, and it's a lot harder to execute. So then when we were thinking about this, we realized that it had nothing to do with determinants. It just is a quadratic form, right? And then you say, well, you're kind of unhappy because the determinant is only a quadratic form for GL2. So, but I mean, Aaron Pollock said to me, well, why not work with other, I mean, like spin groups, right? They have a nice determinant on them. And, you know, I don't understand spin groups, so I decided to do some ad hoc thing with general linear groups instead. And the idea was to try to build something where I could use that quadratic form in some nice way. I don't know anything about it. I don't know anything about a particular term. So, and it doesn't seem to be possible to isolate I mean, you can compute the other terms too. It looks formally sort of like what happens with an Eisenstein series where you have a constant term and you have other terms that are the Whittaker. And you even you see an exponential appearing that depends on beta and whatnot. But then the game is we have to develop a new perspective on how to extract analytic information out of such an object. But the general procedure, I mean, it doesn't even need this Poisson summation formula business. I mean, I think if you look through pre-homogeneous vector spaces, I think that there will be other situations where you can try to not look at spherical varieties, but spherical varieties times something that's simple enough that we can understand. So, yeah. For GLN? So there's no reason that I think that it should. You're going to have to I mean, essentially another way of looking at adding another copy of the U on is that you're adding an Eisenstein series that's a trivial and parabolic Eisenstein series. So instead of adding the trivial and parabolic Eisenstein series on, you would want to add another appropriate Eisenstein series, maybe having a cusp form on a smaller group. So of course I haven't worked out any of that, but I don't see why. And there's going to be the affine space that you're multiplying times is going to get bigger. So in principle, there should be no obstacle to doing that. There's no, I mean, right? So that's the dream that